Imagine walking into the Los Angeles Union Station, right now.
Right.
It is packed. People are rushing everywhere to catch trains, and right there, right in the middle of the concourse, is a fully stocked 24/7 convenience store.
Oh, yeah.
It's got like over 400 different products, and it's serving a transit hub of 60,000 daily passengers.
But here's the thing. There are no cashiers.
None.
There are no managers in the back room. There are 0 human employees. This store was set up by a company called VenHub. It was installed in a matter of days, and it is entirely run, monitored, and optimized by artificial intelligence.
It's wild.
Right. There's no futuristic promise here, no coming soon press release, just an AI doing physical retail autonomously today.
I mean, it is a perfect encapsulation of where we actually are right now. We have this habit of talking about AI as the technology of tomorrow, as if we're still waiting for it to mature,
Oh, absolutely.
We play around with a chatbot or we generate a funny image and we think, oh, we're looking at a neat little preview of what might happen a decade from now. Exactly.
Yeah.
But the reality is that the future isn't in transit anymore.
Mm.
It is fully unpacked, it's moved in, and it's literally rearranging the furniture.
Yeah, it really is.
So welcome to another deep dive. If you're joining us today, you are the learner. You're here because you want to bypass the hype cycle, skip the doom scrolling, and just get straight to the actual verifiable mechanisms of what is happening in technology right now.
And we really have a phenomenal roadmap for that today.
We do. Our mission today is to unpack this massive stack of recent breakthroughs, specifically 15 different discoveries detailed in a new report from AI Uncovered. But, we aren't just going to read you a list of stats.
No, that would be boring.
Right. We're going to connect the dots. We need to understand the underlying mechanisms of how this technology is evolving, because the shift happening right now is, it's profound.
It really is. And just to set the stakes here, we are definitively moving past the era of AI as a conversational parlor trick. The data we're looking at today proves we are entering a phase where AI is building physics-based virtual worlds. It is engineering new biological drugs from scratch. And like you mentioned with the LA train station, it's autonomously running businesses.
Okay, so let's unpack this, because before we can talk about what these new systems actually do, we really need to talk about how they think.
Right, the foundation.
Because the common assumption, and I have absolutely been guilty of this, is that to get a smarter AI, you basically need a bigger, hotter, energy-hogging data center.
Yes.
I always pictured, something the size of a small country, just brute forcing its way to an answer, like plugging a warehouse full of computers directly into a nuclear reactor.
Yeah, and that is the traditional paradigm. Standard CPUs and GPUs, they use incredible amounts of power to process information linearly and heavily.
Right.
But what is so fascinating in this new data is that the hardware paradigm is fundamentally shifting toward efficiency. We are seeing the sudden, viable rise of neuromorphic computing.
Okay, neuromorphic, meaning it's taking the shape or structure of a brain.
Precisely. So instead of the brute force grid of a standard computer chip, these new chips physically mimic the neural structure of a human brain.
Wow.
So they have neurons and synapses that only fire when they actually need to. Intel, for example, has developed a chip called the Loe-2.
Okay.
And for certain complex optimization tasks, it is delivering over 100 times better energy efficiency than a conventional GPU.
Wait, 100 times?
Yes, with latency under a millisecond.
That is incredibly fast. But they aren't just testing this on a small scale anymore, right? You were looking at the specs for that new system they built with these chips.
Right. The system is called HaloPoint. It's a research system that links together 11,152 of these Loe-2 processors.
Okay.
And when you combine them, the system simulates 1.15 billion artificial neurons and 128 billion synapses.
Okay, wait, give me your real-world equivalent here.
Okay.
What is the power draw on a system mimicking a billion neurons?
Well, at its maximum load, that entire system uses about 2,600 watts.
2,600 watts.
Yeah.
My kitchen oven uses more power than that when I'm just baking a frozen pizza.
Exactly. You could literally plug it into a heavy-duty wall outlet. And while it's using the power of a kitchen appliance, it is delivering 15 trillion 8-bit operations per second per watt.
Let's break that down for a second,
All right.
because when I hear 8-bit operations, my brain goes straight to like a retro Nintendo console.
Right.
What does that actually mean in modern AI?
It's a great question. So in computing, the bits refer to how much precision a number has. A 32-bit number is incredibly precise.
Like with a really long decimal tap.
Yes,
Yeah.
exactly. But it is very heavy for a computer to move around. An 8-bit number is a smaller, much lighter package of data.
Okay.
What researchers have realized is that neural networks actually don't need absolute 32-bit mathematical perfection to recognize patterns or generate text. By dropping the precision down to 8-bit, the AI can compute vastly faster using a fraction of the energy, and it doesn't lose meaningful accuracy.
So it's like realizing you don't need a massive diesel-chugging freight train to deliver a single envelope.
Yeah,
You can just use a highly efficient, lightweight drum.
that's exactly it.
But it's not just the physical hardware getting this efficiency treatment, is it? The software itself is changing how it operates.
Yeah, that is the second half of the efficiency equation. Look at the algorithms themselves, like Mistral's new model, the Mixtral 8x7b. This is a large language model with roughly 46.7 billion parameters in total.
And a parameter is essentially a connection in the AI's brain.
Yes. So in older models, to answer a simple question, the system would fire up all 46 billion of those connections.
Which goes back to that whole brute force problem we talked about.
Right. But Mixtral uses a mechanism called routing. When you give it a prompt, it has a gateway that looks at the request and routes it only to the specific parts of the model that specialize in that topic.
Oh, that's smart.
So out of its 46.7 billion parameters, it only activates about 12.9 billion for any given word it generates.
Wow, so it's not firing up the entire manufacturing plant just to produce one single screw. It only turns on the exact machine it needs.
Exactly. And because of that targeted routing, its inference speed, the speed at which it gives you an answer, is about 6 times faster than older, massive models like Llama 2 70B, while using way less compute.
And we're seeing this exact same philosophy applied to how these models actually learn in the first place, too. There was a fascinating study from researchers at UT and MIT mentioned in the data. They built what they call a neurosymbolic system.
Which is just a brilliant hybrid. Traditional neural networks, they're great at pattern recognition, but they really struggle with hard logic.
Right.
Symbolic AI is the complete opposite. It uses strict rules and logic, but lacks any sort of intuition. So a neurosymbolic system combines the two.
And they tested this hybrid system on the Tower of Hanoi. Right, that classic puzzle with the 3 pegs and the discs of different sizes.
Yep, where you have to move the stack without ever putting a larger disk on a smaller one.
Right. Standard AI models really struggle with this because it requires forward planning, not just guessing the next word.
Right.
But this new system hit a 95% success rate.
And the staggering part is how it did it. It used just 1% of the training energy and 5% of the operating energy of a standard model.
Wow.
It took the training time down from a matter of days to just 34 minutes.
Okay, I have to pause on one more efficiency breakthrough because I genuinely need you to explain it to me.
Sure.
MIT has this new framework called Compress-M. The data says it compresses state-space models during training, taking a 128-dimensional model down to 12 dimensions while speeding up training by 4 times and maintaining accuracy.
Yes.
Now, when you say dimensions, my brain immediately goes to, like, sci-fi parallel universes. What is a dimension in this context, and how do you just delete over 100 of them without making the AI stupid?
It's a really common point of confusion.
Yeah.
In machine learning, a dimension is simply a feature or a variable that the AI is paying attention to. So, let's say you are trying to identify a car. The dimensions might be the color, the number of doors, the size of the tires, the shape of the headlights, the material of the seats, and so on. A 128-dimensional model is tracking 128 different variables simultaneously to make a decision.
Okay, that makes sense. So how does Compress-M shrink it to 12?
It uses advanced math to figure out which of those variables actually matter for the specific task at hand. It realizes, hey, I don't need to know the material of the seats or the brand of the stereo to know if this is a truck or a sedan.
Right.
I only need these 12 core traits. So by mathematically squishing the data down to only the most critical variables, the AI just has exponentially less math to do, which is why it trains 4 times faster.
It's like compressing a police suspect description. You don't need to know the suspect's shoe size, blood type, and their favorite movie.
Right.
You just need their height, hair color, and the car they're driving.
Exactly.
If you strip away the noise, you can find them 4 times faster.
That is a perfect analogy. And this ruthless efficiency, in both the silicon chips and the algorithms, is what enables the next massive leap.
Because the hardware and software are suddenly so efficient, We now have the computational breathing room to vastly expand the AI's mind.
Right. Which brings us to the goldfish memory problem. For a long time, talking to an AI was like talking to someone with severe short-term memory loss.
Oh, yeah. It would give you a brilliant answer to your first question, but then, like 10 minutes later, it had completely forgotten the context of the conversation.
That active memory is called the context window. And it was physically limited by how much raw compute it took to hold information in an active state. But look at where we are now. Anthropic's Claude 4 Sonnet handles a 200,000 token context window with less than a 5% loss in accuracy across the entire document.
That's massive.
And it gets crazier. Google's Gemini 3 Pro and Meta's Llama 4 Scout have blown the doors off entirely with 10 million token context windows.
Okay, a token is roughly 3/4 of a word, right? So 10 million tokens. What does that actually look like in practice?
It means you could upload the entire Lord of the Rings trilogy, the complete United States tax code, and a massive corporate software code base into the AI's brain simultaneously.
Unbelievable.
It can hold all of that in its active working memory, analyze it, and cross-reference it in seconds.
And because it has that immense capacity to hold complex information all at once, it isn't just regurgitating facts anymore. It's engaging in deep, abstract reasoning.
Yes, and this is where the implications get very real. Look at DeepMind's AlphaEvolve. It was tasked with solving a fundamental problem in computer science, multiplying 4x4 matrices.
A matrix being a grid of numbers.
Exactly. For decades, human mathematicians have tried to find the absolute fastest way to multiply these grids together. The standing human record was a method that required 49 scalar multiplications. The smartest people on Earth could not find a way to do it in 48.
But AlphaEvolve did.
It did. Using its deep reasoning capabilities, it invented a brand new algorithmic approach and solved it in 48 steps.
Okay, I have to play devil's advocate here for a second.
Sure.
Holding 10 million tokens in your head is a great tangible tool, but shaving off one single multiplication operation in a math problem, that sounds incredibly academic. Why does discovering a slightly faster math trick actually matter in the messy physical reality we live in?
I completely understand the skepticism, but let's look at the mechanism of why that single shaved operation is revolutionary. Matrix multiplication is not just abstract math on a chalkboard. It is the fundamental underlying calculation that makes computer graphics work.
Oh, wow.
It is the math that processes global data traffic. It is the exact math used to train AI models. A computer does this specific calculation billions, sometimes trillions of times a second.
Okay, I see. So if you make that one single operation even a fraction of a percent faster,
you save an astronomical amount of time, energy, and physical hardware globally. By applying AlphaEvolve's new mathematical shortcut, Google actually improved its global data center scheduling efficiency by 0.7%.
that's huge at their scale.
Right. That one math trick sped up the foundational flash attention kernel by 32.5%. And ironically, it sped up the training of Google's own Gemini AI model by 23%.
It's like abstract theoretical reasoning reaching out and directly optimizing the physical power grids of our reality.
Exactly. So if the AI is effectively rewriting the fundamental math that runs a computer server, what happens when you point that exact same mathematical reasoning at the physical world?
You start decoding the physical laws of the universe, which we're seeing happen in real time with disciplines governed by hyper-complex physical laws like global weather systems.
Right. Traditional weather forecasting is incredibly tedious. From what I understand, meteorologists basically overlay a 3D grid onto the Earth and use supercomputers to calculate complex fluid dynamics equations for every single square on that grid. It takes hours to run.
It does. But AI approaches the problem completely differently. Instead of calculating equations, it looks at decades of historical weather data and inherently learns the physics from the patterns. Huawei's Pangu model can now generate a highly accurate global 24-hour weather forecast in 1.4 seconds using a single GPU. It is 10,000 times faster than the traditional grid method.
That's just wild.
And DeepMind's GraphCast does a 10-day forecast in under a minute, beating the industry standard human system on 90% of the test variables.
But the breakthrough isn't just that it can predict reality faster. The truly mind-bending part of this data is that AI is now simulating entirely new realities based on this physics. The industry is calling this world modeling.
World modeling. It's a massive paradigm shift. When most people think of AI video generation, they think of systems that just predict what the next pixel should look like to make a pretty picture.
Right.
A world model is entirely different. It generates an interactive environment with a built-in physics engine. Jan LeCun's AMI labs just raised $500 million specifically to build these platforms. DeepMind's Genie 3 is generating fully interactive, playable environments at 24 frames per second.
But why? I mean, what is the practical application of generating a physics-accurate video game?
Because it creates a perfect, risk-free sandbox for the real world. You can drop an AI agent controlling a virtual robot into one of these simulated worlds. The AI learns that if it knocks a glass off a table, gravity pulls it down, and the material fragility of the glass causes it to shatter.
Oh, wow.
Yeah, it learns physics through interaction, running millions of trial and error experiments in a simulated reality before that software is ever downloaded into a physical robot in our physical world.
Incredible.
NVIDIA's Cosmos platform, which does exactly this, already has over 2 million downloads.
And it isn't stopping at physics. It's hacking biology, too. This was the part of the deep dive that genuinely made my jaw drop. Researchers at TU Darmstadt used deep learning to design something called a riboswitch. They made this biological component function exactly like a Boolean NAND gate.
Which is just a beautiful conceptual bridge between computer science and biology.
Yes.
In computing, a NAND gate is a fundamental logic switch. It basically says, output a signal unless both input A and input B are present. If both are present, turn off.
So how does an AI build a logic gate out of biology?
By treating living cells like programmable hardware. The AI sifted through thousands of complex RNA sequence combinations to find the exact specific way an RNA molecule needs to fold in on itself.
Okay.
It designed a custom RNA structure that acts as a physical switch. It will literally turn a living gene's expression on or off based on the presence of specific chemical inputs.
Meaning you could theoretically program a living cell to release medicine only if it detects two very specific disease markers in the body.
Yes.
And if the markers aren't there, the gate just stays closed.
Exactly. The AI narrowed down the possibilities so accurately that the human scientists only had to test 82 variants in a physical lab to find the one that worked flawlessly.
AI is basically treating biology like a massive software code base that just needs to be debugged. We saw the precursor to this when DeepMind's AlphaFold 2 predicted 200 million protein structures in a single year.
Which is crazy.
That is an amount of experimental work that would have literally taken human scientists 100 million years to complete manually. And now, companies like In Silico Medicine are using AI platforms to cut the timeline of drug discovery from 5 years down to 18 months. They are only needing to physically test about 60 compounds out of the 15 million the AI generates, saving potentially $2.8 billion in research per drug.
Which naturally leads to a very profound question about the future of human discovery.
Yeah, like what happens to the human scientist? If the AI can do 100 million years of research in a calendar year, do human researchers just hang up their lab coats and sit back to watch?
Not all. The role of the scientist is simply evolving. They're transitioning from being the person doing the manual, tedious pipetting at the workbench to the person directing a superintelligence.
Right.
To facilitate this, the U.S. Department of Energy is currently building billion-dollar AI-focused supercomputers machines named Lux and Discovery. These aren't built to replace scientists. They're explicitly designed for human researchers to wield AI like a powerful lens, driving breakthroughs in nuclear fusion and advanced materials 10 to 100 times faster than before.
Okay, so we've seen AI master physics, rewrite biological code, and invent new math. But let's bring this immense power down to earth, right into the typical corporate office. Think about your own Monday morning workflow, your own inbox, your project deadlines. What happens when you drop this raw reasoning power into the workforce?
You witness the transition from AI as a reactive tool to AI as an autonomous colleague. We are entering the era of agentic AI.
Let's define the mechanism there. What is the actual difference between a tool and an agent?
So a tool waits for you to swing it. If you ask a standard chatbot to write an email, it writes the email and goes to sleep. It requires your constant prompting.
Okay.
An AI agent operates on a continuous loop. It can be given a high-level goal, like research these 10 client websites and generate a customized pitch deck for each.
Right.
The agent makes a plan, executes the first step, observes the result, adjusts its strategy if it hits a roadblock, and continues working autonomously until the entire project is finished.
And according to Gartner, by 2026, 40% of enterprise applications will feature these task-specific agents. The market for this software is jumping to $52 billion by 2030. But the crucial shift here isn't just a single agent working alone, it's AI systems working in teams.
Yes, multi-agent frameworks. You have one AI acting as the researcher, passing data to an AI acting as a writer, who passes it to an AI acting as the editor, with another AI playing the role of the project manager overseeing the whole workflow.
These are literal digital coworkers. Take Coz AI's new agent named Junior. The demand is so intense that they currently have 2,000 corporate companies sitting on a wait list just to get a software demo.
That's wild.
Because Junior is currently writing 80% of its host companies' code, it initiates half of their sales calls and manages 80% of internal communications.
Wow.
Or look at coworker.ai. Last year, they generated $2.9 million in revenue while employing only 26 humans.
And this autonomy extends beyond software, too. Think back to the VenHub Smart Store at the LA Union Station we discussed at the start. That is an AI agent managing physical inventory, optimizing supply chains, and processing transactions in the real world 247.
Oh, absolutely.
Or look at the experiment run by entrepreneur Reindu Himana. He handed complete control of his software as a service business over to an AI agent for 30 days. He completely stepped away.
And what happened?
In that month, the AI autonomously negotiated and closed a $12,000 annual contract with a client and boosted the company's total monthly revenue from $32,000 to $45,000.
Unbelievable. So if you are listening to this, this is the new baseline reality. The skill you need isn't just knowing how to write a clever text prompt anymore. The skill of the future is knowing how to manage, direct, and collaborate with a team of AI agents.
It is a fundamental restructuring of how human capital is deployed. But, as we zoom out and look at this massive paradigm shift from energy-sipping artificial brains to decoding the laws of physics to autonomous digital employees closing sales deals, there's one final glaring contradiction in the data that we really must acknowledge.
Right. It's the tension between capability and public perception.
Exactly. On the corporate side, the financial commitment is absolute. According to projections by Pantera Capital, U.S. hyperscalers, the massive tech giants, are expected to spend over $650 billion on AI infrastructure in 2026 alone.
$650 billion in a single year.
Yet, at the exact same time, a recent public survey revealed that general trust in AI has plummeted. In a single year, public trust dropped from 43% down to just 27%.
It is an incredible paradox. The technology is vastly more capable, it is remarkably more energy efficient, and it's more autonomous than at any point in human history. Yet humanity is significantly more skeptical and distrustful of it than ever before.
Right.
It's almost like an uncanny valley of competence. Like the better it gets at doing human things, the more uneasy we feel about it. But I gotta say, thank you so much for bringing the data and helping us decode the mechanisms behind all of this today.
Oh, it is always a pleasure to unpack the mechanisms. The reality is that the technological landscape is simply moving faster than our societal ability to comfortably process it.
Yeah, that's so true.
And on the note of moving incredibly fast, I want to leave you with one final thought based on the breakthroughs we've connected today. We have established that AI can now generate highly accurate, physics-based, simulated worlds. And we've established that AI can collaborate in autonomous multi-agent teams. So think about this. What happens when you take an entire team of autonomous AI agents, acting as world-class researchers, and you place them inside a highly accurate AI-generated simulated reality? What happens when you ask them to conduct 1,000 years of simulated scientific research over a single weekend? At what point does the sheer speed of AI self-improvement outpace humanity's ability to even comprehend the discoveries it is handing us?